In the previous lesson, I showed you an algorithm for the knapsack problem which computes an exact solution for the case where all the item values are integers. In this lesson, we're going to look at the case where the item values can be anything. And for this problem, we're now going to give a p-TAS. So what we did previously was an exact algorithm, but here we're going to do an approximation algorithm. And the global strategy is going to be as follows. First, we're going to take our items and actually replace the value of each item, which was value of xi, by a new value, value star of xi. And the idea is that this value star is going to be an integer, and hopefully these integers are not going to be too large. Okay. Then in step 2, well, now we have an instance where all the values are integers. So what we can do is solve this problem exactly using the algorithm we derived in the previous lesson. Okay, and remember, this algorithm had a running time of n, number of items, times the total the total value of all the items. And that's why it's important that in step 1 we actually get integer values that are not too large. Okay? After solving our new problem for these value stars using our dynamic programming algorithm from the previous lesson, we're now simply going to say, okay, take exactly the same items, but now with the original weights, and report this as the solution to our problem. Okay, so the first thing we're going to do is look at step 1. In which way, what is a good way to replace the values by some new value star, which is a small integer. Okay, so the first obvious way would be to say, okay, simply look at all my item values. So for instance, here I have an item of value 4.4, here I have another item, and so on. And now, well, we want integers, so let's simply round every item value to the nearest integer. Okay, so that looks like this. We have all the item values, and we simply round them to the next integer. Okay, we round them up, let's say. Well, unfortunately, this simple approach doesn't work. Why does it not work? Well, there are two problems that we have. First is that these values can be very large, right? They will be integers, but remember that the algorithm we derived in the previous lesson, its total running time depended on the total value of all the items. And if these values are now very large, we will get a very large running time, which may not be polynomial in the input size. So that's the first problem. The second problem is that actually if we do it like this, we have no control over the error that we get. Right? Obviously, if we replace all the values by value star and now compute an optimal solution for value star, well, that may not be the real optimal solution. We will get some kind of error in the solution. And somehow we want to control this error, and if we simply round to the next nearest integer, we do not have any control over these errors. So instead of this, we do something else. And that's the following. So what we're going to do is we're going to first round every item value to the next multiple of delta, where delta is some value, and the choice of delta will be quite important, but we'll discuss that later. So for now, let's suppose we have a good delta. What we're going to do is we're going to round each value to the next multiple of delta. So that's what you see here. Okay? After doing this, well, if we round them up, then of course they can still be very large. So now we're going to scale the whole problem, you could say, by dividing everything by delta. Okay, and note that this also means that we now have integer values. So for instance, what you see for the items, all the items whose value would be in this blue interval, they would all get a new value star of 6, because they round it to 6 delta, and then we divide by delta, so the final value star will be 6. And the way you can compute this value star is using this simple formula. You take the value of xi, the original value, divide by delta, and then round it up. Okay, so let's look at how to pick this delta. Well, remember that the approach that we had is, well, we round everything up to the nearest multiple of delta, and then after that, we divide by delta. So remember that for a p-TAS, the approximation that we want to get has an error term that is dependent on some epsilon. And in particular, given an epsilon for a maximization problem, we want the value of our algorithm, alg, to be at least 1 minus epsilon times opt. Or in other words, opt minus epsilon times opt. Okay. If you look at it like this, opt minus epsilon times opt, then you realize that epsilon times opt you could view as the error that we allow to make. Okay, so the total error that we are allowed to make in our solution, if we want to get a p-TAS, should be no more than epsilon times opt. Okay, now if you remember how we did the rounding, well, you see that everything in an interval, you could say, of size delta is rounded up to this next largest multiple of delta. So the total shift, you could say, or the total error on a single item is at most delta. Okay. After that, of course, we actually divide everything by delta. So it's a little bit tricky whether this argument actually works, but as we will see later when we will do a more precise computation, this intuition that we have here is actually the correct one. Right? And the idea is that if I divide everything by the same amount, I simply scale my problem and nothing happens. So in that sense, the division by delta in the end is not so important. What determines the error is that actually first, when we round everything up, we change the values by at most delta. Okay, so the error of a single item is at most delta. We want to have a total error of at most epsilon times opt. So what do we get? Well, in a solution we have at most n items, right? Obviously we cannot select more than n items. So if a single item has an error of delta, then if you look at the total solution, then the total error will have the total error of the whole solution will be at most n times delta. And this, as we said before, we want to have at most epsilon times opt. So I want to choose my delta such that n times delta is at most epsilon times opt. So I could, for instance, simply take delta is equal to epsilon divided by n times opt. Okay, so let's look at our algorithm. So what we did first was we were going to replace all the values by value star. Okay, and well, we just saw how we were going to do that. We're going to take this particular choice of delta. So delta is epsilon divided by n times opt. And now for each item xi, I define value star to be the original value divided by delta rounded up. Okay, now I have a set of integer values, and let's denote by x star the new set of items, or actually I should say the old items but with the new values, the value stars. And then in step 2, I'm going to use my exact algorithm, my optimal algorithm for integer values on this set x star. And then that will give me a subset, and I'm simply going to report that subset as my final solution. Okay, so this is the plan. But there's a slight problem, namely in step 1, we define this delta in terms of opt. Right? Opt is the value of an optimal solution, but we don't know opt. So that means that doing this in step 1 is not possible for the algorithm because the algorithm does not know opt. So what do we do instead? Well, instead of working with opt, we're going to work with a lower bound on opt. So we're first going to compute a suitable lower bound, LB, and then for delta, we're going to pick epsilon divided by n times LB instead of epsilon divided by n times opt. Okay? And note that because LB is a lower bound on opt, right, it's smaller or maybe equal to opt, that our delta is getting smaller. And that's actually good because delta was our error, right? And if we make the error smaller, that can only be good for us. So replacing opt by LB, by the lower bound in this way, will actually not harm our approximation ratio. Okay, so now the only question is, which lower bound do we need? Or which lower bound can we use? Well, here we're going to have a very simple lower bound. And the lower bound is the following. If you simply take the maximum value of any of your items, well, then as a solution, I could always just take that single item. Right? And here I assume that there are no items whose weight is bigger than W, right? Because such items are completely useless. I'm not allowed to take them anyway. So before we do anything, we just throw them out. And so if all our items have a weight at most W, then the maximum value of any of my items is obviously a lower bound on the best subset that I can get. So this is going to be our final algorithm. Okay, so what we'll do in the next lesson, we're going to analyze this algorithm and we're going to prove that it's a p-TAS. And to prove that it's a p-TAS, we need to prove two things. First of all, that the quality of the solution is good. In other words, that the value is at least 1 minus epsilon times opt. And also, we need to prove that the running time is polynomial in n.